Welcome. Please take your seats. The program will begin in 5 minutes. Kafka Summit London is officially open. Please welcome today's MC, Head of Kafka Developer Experience at Confluent, Tim Berglund.
Good morning. Good morning. Look at this room. This is a full room. We were here a year ago, and there weren't this many people here. This is fantastic. I'm so glad to see you here. In fact, this is off script, but we need a selfie. It's just, I'm sorry. I can't resist. So we're going to do that. Everybody, if you could please wave. There we are. All right. Thank you. Thank you. Now, boy, there's a lot to talk about. To make an event like this happen requires, first and foremost, you. If there's no community, if there's no people, it doesn't even make sense. So really, you come first here. But to put the program together, this is about, it's about food, it's about games, it's about a lot of things. It's about content, right? We come here to learn and to work with each other. And for this to work, we need a program committee to make good selections. We've got an amazing program put together for the next 2 days, and it's really these folks who have done that work. So huge round of applause for our program committee. They are, of course, well compensated for their work. Just kidding, no. But no, they do put in a lot of time to make this happen. And speaking of community, I'm really excited to announce this. This is a thing that some of the folks I work closely with at Confluent have been working on, and that is an MVP program. So there's this little URL down here, confluent.io/nominate. If you know somebody who has been investing heavily in the Kafka community, they've been teaching, they've been writing code, they've been sharing knowledge, whatever it is they've been doing, go to confluent.io/nominate. We'll have a blog post about this tomorrow that tells you a whole bunch of more stuff. But this is going to be great. This is a way, and you can nominate yourself if you want, but it's a way to recognize your peers or just recognize yourself if you're into that kind of thing. To highlight the people who have invested in this community and make this kind of thing happen. Now, Wi-Fi. This is very important. I think most of you, this is on the back of your badge. It seems like most of you are already on the network. If you're not, check this out. Let us know if you experience any problems, and we will turn up the valve on the pipe and make that happen. But Kafka delegates, and the password is Kafka LDN. You want to be on that network because there's some things you need to do. Notably, if you have not yet downloaded the mobile app, you should. There are a few things on the mobile app that you want. The schedule, so you can figure out where to go and who to see. You can create an agenda. You can rate speakers, which you must do. It helps, in particular me, it helps me out a lot to know how the sessions go. That helps us plan future summits and make them better all the time. So please download the app. Check out everything that's in there. It's all gamified. You can win valuable prizes. Also of note, the code of conduct is in the app, and I would encourage you to read that. It's really quite sensible. There's probably nothing in there that's a big surprise. If there is anything in there that's a big surprise, find me and we'll get coffee and we'll talk about life and how to live it well. But it's probably not anything shocking in there, but I would encourage you to check it out. And importantly, kidding aside, if you see anything that violates that, find one of the people in the turquoise shirts that say staff, streaming staff on them, and they can help you with those escalations. So just check that out. Very important to me that you tweet the event. Hashtag Kafka Summit. Please, for all your tweets, all your Instagram story posts, whatever it is you do on social, use that hashtag. Undocumented on the slide, but if you're posting a selfie, you also want to use the streaming selfie hashtag. It's important. I want to see who leads in streaming selfie by the time we're done. All right, with that housekeeping in hand, I would like to welcome to the stage our first presenter. We have 3 talks for you lined up this morning. First, though, I'd like to welcome the co-creator of Apache Kafka, the co-founder of Confluent, Neha Narkidi.
My God, London, welcome to Kafka Summit. Isn't it quite amazing that just at the second London Summit, we have over 1,000 people in attendance? I'm really excited that the London Summit is where I'm getting a chance to speak about our cloud journey and some exciting updates about Confluent Cloud. So let's get started. You know, as part of my job, every day I get to experience a new business reality. And the contrast with how businesses used to work is really quite stark. For instance, you know, in the past, enterprises would think of technology as a support function. The CIO was thought of as a technical leader. But today, technology is the business. The CIO is a business leader. Every day, I get to see major banks that see themselves as software companies that just happen to deal with money. Major retailers see themselves as data companies that just happen to sell shoes. You know, in the past, innovation was sort of thought of as a growth investment, something that was optional. But today, innovation is pretty much core to survival. If enterprises don't reinvent themselves through technology, they might lose. In fact, I was looking at some estimates that over the last 5 years, over 185 retailers have downsized or even shut down in the UK, leading to the closure of over 7,000 stores. You know, in the past also, running the business on yesterday's data was thought of as, you know, good enough. But today, running the business on yesterday's data is pretty much a path to failure. Companies need real-time, modern data infrastructure. And this need for modern real-time data infrastructure is really, I think, the impetus behind event streaming. Some of you might know that Apache Kafka and event streaming was born at LinkedIn back in 2010. Since then, it's spread rapidly within and beyond Silicon Valley to today, where roughly about 60% of Fortune 100 uses it as a fundamental technology platform. Even today, the new companies that get created, the digital ones, use it as a basis for their business. And here's what all of us are building with event streaming. These are some of my favorite applications that have been shared by community members at various Kafka summits and beyond, from banking assistance, publishing pipelines, all the way to online dating. The impact of event streaming spans all kinds of industries, from startups to the biggest established companies. And across each of those event streaming applications, there is a common thread. And there's one central challenge, which is connecting your applications with data. If you remember, in the past, we had roughly 2 ways to do this. We had ETL tools that tracked what has happened in the world. And we had messaging systems that helped us track what is happening in the world. And we had these 2 ways of connecting applications with data, and we applied it to a brand new environment. And this is how it plays out, right? You have ETL tools that connect your data systems, primarily databases, data warehouses. You have then your messaging systems. You introduce it to connect your applications in real time to track what is happening. Then you want to connect across lines of businesses so you can build meaningful applications, so you introduce more connections. And nowadays, you want to adopt the public cloud, so you end up with even more connections. Ultimately, this is what every enterprise data infrastructure looks like when we talk to them. And this is the ultimate visual representation of what it means to be restricted by infrastructure rather than being enabled by it. But then how did we get here? You know, it's because of trade-offs that were introduced by the technologies that existed back then, right? If you think about this, the ETL and data integration model allowed you to move large amounts of stored data at high throughput. It is durable, it's persistent, it's ordered. But it also meant doing batch processing, which is expensive and time-consuming. So you have that on one hand. On the other hand, we had messaging systems, and they're meant for communicating in real time between applications, so it's obviously fast and low latency, but then it's sometimes hard to scale for high throughput use cases. And most importantly, there is no persistence. So after consumption, there is no way to go back and replay to fix things. So both of these models have their inherent upsides and downsides, but the situation is actually far worse. As you've seen, we've built a whole maze, but we still haven't solved the core problem, which is how do you build these real-time, data-driven applications that could span the whole organization, that could break infrastructure and various organization boundaries? The answer is in event streaming. The event streaming paradigm, what it does is it takes the strengths of both of these two very different ways of handling data, and it builds from the grounds up a modern technology platform, one that is highly scalable, it's durable, it's persistent, ordered, it's also fast and low latency. Now, instead of answering these two separate questions of what has happened in the world and what is happening in the world, you can now answer a single and much more important question: what is contextually happening in the world? And why is this contextuality important? Let me take an example. On the screen, what you will see on the left is a mobile location tracking application. You'll see a red arrow, which is the car. On the app, you will see real-time location as well as the speed of the car. This is an event-driven application, and because it uses real-time information, you could possibly build it using some messaging system as long as it could scale. On the right, you see the ETA app by Lyft, one of our largest Confluent Cloud customers. This is a contextual event-driven application because Lyft builds it by combining real-time information with historical data on traffic access patterns. Now, the reason I make this distinction is because there is an entirely different level of value that can be achieved with these contextual event-driven applications. And if you request a ride to the airport, it is certainly valuable to know, the location of your driver, but it is much more valuable to know when the driver will actually get to your house. That is the value of a contextual event-driven application. The fact that you can marry real-time data with historical context actually makes all the difference. Now, event streaming isn't just about a foundational technology change, but you have to fundamentally rethink the notion of data itself. The event streaming paradigm rethinks data not as stored records or as transient messages, but as a continually updating stream of information. Essentially, a never-ending stream of events that is both stored and is continually kept updated, giving you both a real-time view of your data, but also full history of how your data has changed over time. Many of you will recognize this as nothing other than the core construct of event streaming, which is the continuous commit log. Once used in a company, event streaming gets you this universal event pipeline. This can scale to the scope of an entire organization. It could break infrastructure boundaries. It could break various organization boundaries. But much more importantly, it allows you to build these contextual event-driven applications that could really change how the business works. And all this is powered by Apache Kafka, which acts as the organization's central nervous system. So now that you know about event streaming, I want to transition to how you can succeed with event streaming. And here I want to speak about our cloud journey, things we learned from being one of the largest operators of a fully managed Kafka service. And this sort of operational knowledge of running Kafka has had to scale with the growth of data and traffic to our fully managed service. In fact, just today, we will be onboarding a new customer who said they would like to do more than 25 gigabytes per second over the next several months. So at this rate, maybe this time next year, at the next London Summit, this number could be frighteningly about 100 gigabytes per second. The point here is that when this sort of scaling happens in a relatively short amount of time, you end up learning quite a lot, and your systems just have to evolve. And so evolving Confluent Cloud over time hasn't been easy. We've encountered a number of obstacles along the way, and what I want to do here is share some of the key lessons that might be helpful to you as you take this event streaming journey. So the first one is there is no cloud-native easy button. So what I mean by this is becoming cloud-native, if you didn't already start there, it doesn't happen overnight. It is a multi-phase journey. And I like to compare it with traveling. Becoming a cloud native could be compared to how can you become a good traveler. What you have to do is to learn how to pack smart cloud containers, to learn to speak local languages, Kubernetes, Cloud Foundry, to change your cellular plans, cloud networking, to get local currency, cloud billing. You have to buy maybe a money belt to avoid pickpockets, cloud security. And much more importantly, bring along some of your personal belongings, your data. And that last part, bringing your data, is quite relevant to event streaming. Now, if you have to start this cloud-native journey, the first step is building a production-grade application in the cloud. And in order to do that, you have to bring along some of your data, so you can start experimenting with that. So synchronizing streaming data between on-premises and cloud environments is, as you might know, a pretty good use case for Apache Kafka. So when our customers asked us to solve this problem, initially we thought just about copying data in Kafka, and we thought that would be sufficient. But as we helped people do this, we learned quite a few more things, that just copying data in Kafka is not sufficient. You also need to copy schemas that go along with that data, so you can actually evolve that on the fly. The second thing we learned is that people didn't want to just do a blind copy of all their data in the Kafka cluster. They wanted to selectively and securely copy some topics over. That wasn't just about moving data in user topics, but in order to migrate consumer applications with minimum manual effort over to the public cloud, we also needed to migrate consumer offsets and so on and so forth. So over time, we added all that functionality to Confluent Replicator. But the point here is that the applicability of this lesson isn't just limited to hybrid environments, but it also extends to multi-cloud environments. And that is really relevant now. A recent survey of over 700 IT executives in the Wall Street Journal noted that over half have either adopted or have plans to adopt hybrid and multi-cloud environments. And the reason people want to do that is because there's a trend to use best-of-class services versus going all in on one public cloud. Right, moving on to schemas. Schemas are the service APIs for event streaming. Now, changing the date field from December 1st, 2015 over to a timestamp can look like a perfectly innocent change. So if all the unit has passed, you can just ship this, right? Well, not too fast. As Uber found in this case, and many other companies in other cases, this seemingly innocent change could break multiple downstream consumers that were simply not ready for this format change. So the point here is that just like APIs, schemas of events produced to Kafka are like contracts between the event streaming services. And just like any other API contract, schemas need to be discoverable and searchable, versioned, validated, and enforced. Companies that discover this requirement, they turn to the schema registry pattern, a central service that stores all versions of all schemas of data produced to Kafka, allowing users the ability to discover and browse schemas, validate the changes, and then enforce the compatibility of future changes in production. This needs a central schema registry across all your Kafka clusters that you can configure to be both forward and backward compatible. So you can make upstream or downstream changes, or even changes to Kafka itself, without breaking a thing. But the most interesting thing is that having first-class schema discovery, validation, and enforcement, it actually opens the doors to future really exciting use cases. The ability to do broker-side validation, ensure required fields, and maybe even track data lineage. Moving on to stream processing. And if I'm being honest, developing stream processing applications can be surprisingly tricky. It is a different way of writing a program. It is a different programming model. And with all that change, sometimes there can be gaps in how you develop your program. For example, when data is in motion in a stream, it can sometimes be hard to see how your application processes all those events. All kinds of problems can occur, from signature mismatches to serialization errors, or maybe just that your processing logic didn't quite do what you expected. Take KSQL, for example, a streaming SQL engine for Apache Kafka. In the past, you might write some queries on Kafka topics, and if the queries didn't quite do what you expected, you might have to scroll through different Kafka log files or attach low-level Kafka consumers to figure out what has happened. As you write hundreds of queries across multiple applications, this can sometimes be pretty untenable. And so we thought hard about what a great observability experience for something like KSQL could look like. Something that allows you to stay within the same paradigm. We thought, what if you could use the same tools to observe your stream processing program that you use to write it in? Wouldn't that significantly lower the cognitive load of figuring out your problem? So that's how we came up with the KSQL processing log. As KSQL executes a query, it writes records to a processing log that details how it processes every single row, including any errors that you encounter along the way. The important thing is that these log entries are structured events. Yes, they have a schema. So you can actually consume and query the processing log using either a consumer or KSQL itself. So that means you can use the KSQL grammar to actually debug your KSQL queries. And as this example shows, that using this tool, it became much easier to pin down that root cause of all those nulls in your query response back to an upstream serialization error. We knew that scaling our cloud service from 100 megabytes per second to a few gigabytes per second in just a few months was not going to be easy. And this isn't just about sustained growth, but it's about those traffic bursts where you have to allow instantaneous scaling for only a short period of time, followed by downscaling so you don't have to pay for all that unused capacity. And all this meant a serious investment in service elasticity. As we worked on making Kafka elastic in the public cloud, we actually ended up solving a few more problems than we had previously planned. And the first is that elasticity means providing instant access to capacity and also the ability to scale it instantaneously, which pretty much means that there is no time to size or resize clusters when you're experiencing a traffic spike. So we had to get rid of that. The second thing is, when we thought about service elasticity, we only thought about Kafka. But as we worked on making the service elastic, we actually ran into all sorts of limits that the cloud providers rightfully have on their infrastructure. Limits on the number of VPC, limits on the number of ELBs. We had to build and rebuild our control plane to work around all those limits in an automated fashion. That took a while. When you design a service that allows for traffic bursts, but also needs to keep several nines of uptime, you also need to balance data in a Kafka cluster, not only intelligently, but also in a continuous fashion. And just like our users store data in Confluent Cloud for weeks, sometimes months, the ability to do continuous load balancing also means making sure that you have much less data to move around. As you're experiencing a spike in doing load balancing, you just have to move data out of local storage. So last but not the least, life is better without cluster sizing. Now, did you know that one of the most frequently asked questions by Kafka operators still is, how many brokers do I really need in my Kafka cluster? And that goes on. How much storage do I need per broker? How do I configure the brokers to actually use all that capacity in the most efficient manner possible? Yes, cluster sizing is a hard problem. It needs a lot of expertise, benchmarking of various kinds of workloads, ongoing capacity planning to make sure that you have enough capacity that you need for your growth. At least on premises, you buy machines infrequently, so you have to make some of these choices only once. But in the cloud, you have to keep remaking these choices, keep up with ongoing change. And all this means, for some of us, getting things wrong and picking between two difficult options. You over-provision, or you deal with an outage. And why are you posed with this difficult choice? It's because of several reasons. The first is that sizing in the public cloud is a moving target. You have to make lots and lots of choices between number of instances, cloud options, networking options, number of ELBs, and so on and so forth. By the time you've mastered all those changes, they've released something new. And if you plan to adopt multiple clouds, you can just do the math on the complexity. The second is that understanding cloud infrastructure costs can be surprisingly tricky. And sometimes even the cloud providers document it incorrectly. There have been instances when we had to debug Kafka network pricing in a way that we notified them to update their docs. That was good for the service and for us, but it took multiple days of investigation. And when you self-manage multiple data services in the public cloud, understanding cost attribution of any particular service is even harder. There are so many times when I encounter Kafka operators that incorrectly understand the cost of operations of their own Kafka cluster. So all this means that our observation is that even people who have operated Kafka for years actually find it pretty hard to find the right cloud infrastructure to run it efficiently over time. And obviously, no one loves an outage, so you generously over-provision your Kafka clusters, sometimes massively more than you even need. Just this typical example of a Kafka workload, that shows that you have maybe a couple of choices to make between instance sizes and networking options, whether it's VPC peering or private link, or a storage option between EBS and SSDs. That just the cost of those decisions in the differential can run more than $1 million per year. Of course, the absolute cost could be much more. So this is a big problem. So those were some of our top lessons learned while operating Kafka ourselves for years at large scale. For those of you who are self-managing Kafka clusters, be it on premises or in the public cloud, I hope that these lessons help you along your own event streaming journey. And for those of you who prefer to just lean on a fully managed service, Confluent Cloud might be the right place to start, especially today. I'm really excited to announce a major step forward in making Confluent Cloud an elastic cloud-native event streaming service. Cloud today will allow you to elastically scale Kafka workloads from 0 to 100 megabytes per second instantaneously and down, without ever having to size or provision a cluster. You can scale beyond that to tens of gigabytes per second with a provision capacity model in our enterprise offering. Cloud now allows you to only pay for what you actually stream versus what you think you might use or over-provision peak cluster capacity. You might use the service for a couple days, not use it for a couple months, and not have to pay for all that unused cluster capacity. There are no minimums, and a realistic but small production workload could cost you roughly $50 a month. And what I'm most excited about is that we're also fully managing several popular Kafka tools. Now you can get schemas for free out of the box. You can pipe data from Kafka into S3. You can write KSQL queries over some of your Kafka topics. These features are still in preview, but we're looking for your feedback. So give it a spin and let us know what you think. And here's a quick visual of that simplified experience. As you can notice, you put in the name of a Kafka cluster, you pick a region, you confirm a credit card, and that's about it. Now you can point your clients to a Kafka cluster and start streaming. There is no need to size clusters. There's no need to think of traffic bursts. And we're really stoked about this 5 seconds to Kafka experience. We hope that you can try it out. If you do choose to try it out, there is Confluent Cloud, but there's also Confluent Platform, which is a self-managed software download. If you choose that option, I'm also happy to announce that all the features, including the commercial ones, are completely free on a single node. So before we conclude, I want to pose this question. Just take a moment and think about, what are the possibilities if we could all succeed with event streaming? Every day I get to see event streaming transform the biggest industries out there. For example, event streaming is really disrupting transportation. How many of you remember the days when you had no knowledge of driver arrival, you had no data on sensor diagnostics? Today we have real-time ETA, real-time driver-rider matches, real-time sensor diagnostics, all powered by event streaming. Event streaming is transforming banking. How many of you remember the days when you had out-of-sync account information? Banks had to do fraud detection and internal risk reporting in batch. Today we have real-time omni-channel account updates. Banks can do real-time fraud detection and internal risk reporting, all powered by event streaming. How many of you, remember the days when you had out-of-stock emails after placing an online order, you had no real personalization? Today we have real-time inventory across web, mobile, and store, and real-time contextual recommendations. Event streaming is truly transforming every industry out there and will continue to do so in the next few years. But just how big is the impact? 10 years ago, the major cloud vendors shaped the future of the data center by reconceptualizing infrastructure as code. Today, event streaming is reconceptualizing data as a continuous stream of events, making event streaming paradigm truly the future of data. Thank you very much.
Thank you very much, Neha. Next up, a quick question. How many of you watch television? Hands up, please. I think probably, okay, so some of you. All right, so I'm gonna guess a significant, that's interesting. We don't know each other, but I'm guessing a significant fraction of those of you who do take advantage in one form or another of the systems that our next speaker builds. I'm going to welcome in a moment Keith Davidson. He's Director of Group TV Distribution Platforms at Sky Group. This includes live streaming, video on demand, a bunch of analytics things, a lot of exciting things. And when you build systems, you build things on Kafka at that scale, there's a lot that those teams learn, a lot of specifics, right? A lot of Neha was talking about what it's like to build a cloud service at scale. And when you build things out of Kafka, large things out of Kafka, you learn a lot of details. Well, Keith's going to take a slightly different approach. He's going to talk about how this effort has transformed the organization. So, Keith, welcome.
Good afternoon, everyone. It's great to be here in a community of developers, engineers, and technologists. So I want to take this opportunity to discuss what I think is probably one of the hardest problems we have in engineering. Now, you may think that's, when I started out, the hardest problem I thought I had was trying to fit my control system for a telephone exchange into 4K of memory. Now, that might give you a little idea of how old I actually am. Or it may be that you're trying to define consciousness within software, AI systems. Yes, these are hard problems. However, I think actually the hardest problem is how you develop a culture and facilitate developing that culture to solve those problems. That's actually probably the hardest problem from my point of view. So it's a non-technical problem. You guys will be talking about lots of technical issues, technical problems, how to solve them through the day. So we're going to go through a non-technical one. And it is how Kafka, as one of the tools we use, has helped us through that journey. So when we look at culture, and we look at how we develop our products, how we develop them so we can delight our customers. In Sky's case, it's how we get content to the customers in the way that they can access it and see it, and effectively have the content they love to see, seamlessly, easily. So, to develop a culture, what do you need? Well, first of all, let's define the problem. Because what is culture? Culture is a set of norms. It's a set of values which you share within a group of people, and you repeat, as Aristotle said. We are what we repeatedly do. So how do we actually, you need to be able to repeat the things, make them habit. This may sound familiar. It's like agile development. You repeat, it becomes part of what you do. But also, there's another aspect. When you look at the cultures, they are affected by the tools you adopt. And as you shape the tools you use, it will impact dramatically what you produce. If you think in the case of, go back in history again, Linux when they first started out, if it wasn't for the ability to pipe between commands, the way that system would have been developed, I would propose, would actually have been fundamentally different. You would have probably ended up with lots of monoliths. Yet, that simple function of being able to pass information from one command to another allowed developers to develop specific commands for specific purposes. So, again, part of culture, from our perspective, is when we create the tools, those tools will shape us and affect our culture and affect the way we produce our services. So why is this so important to us? Well, another aspect of it is that the culture you have within your organization, particularly your engineering culture, will come through in your product. So as it comes through in your product, your customers will see it, they will experience it. Maybe not directly, but indirectly. So the scalability of your product, the engineering principles you have behind it, all the things which make it a value to them, they will see. And it will affect the value of your organization. So that's one part of the problem. You have to be able to establish a culture which is repeatable, a common set of values. You have to have tools that support that and actually feedback and allow it to continue. Now, one thing you have to be careful here, particularly around the tools, is we've all seen it in our industry where the tools take on the life of their own. It's all about the tool, and it almost becomes religious. I will use this for the solution. One of the parts of our culture is also you always have to be able to challenge it also. And I'll talk through a little bit about how the introduction of Kafka was a challenge to a culture and modified what we actually did. So always be open to that challenge is also part of the way to build a successful culture and ultimately, I believe, successful products. So, couple of problems there to solve. Next problem is as you scale, as you increase the culture and how you're trying to spread it across the organization, Conway's Law comes in. Now, what this does is, and this comes back to how you organize yourself reflects in your product. It will, your products and your designs, your architecture will start reflecting the organizational patterns within your organization, and particularly around the way it communicates. So when you talk about things like how interfaces are defined, how contracts are defined between one service and another service, those will form around the organizational structure you have. It will start taking on that persona. Now that may be okay. You organize through your architecture. Fantastic. So you organize your teams, you're orientated around your architecture. There is, however, one problem with that, in my experience. We are in an industry which is fundamentally about change. You could redefine our industry as change everything all the time. There's new technologies coming along, new features required. Customers, as they use your product, will evolve, and we will have to provide other features, functionality, other services to them. So suddenly, you start becoming constrained and your product very rapidly will stop developing because your organization is set around this way. So how do you overcome this? So to us, that's the problem. You need to build a culture. You need to be able to ingrain it within the organization. But you've also got to stop the organization from changing and constraining you from actually developing the solutions that your customers actually require. So we believe that you have to hack Conway's Law. So the way we do this, and the key to it, is communications. The way we believe you can overcome this is you abstract away the way in which the organization communicates and the way in which your systems communicate. By doing that, you free yourself from Conway's Law. A lot of things have to come into play for that, but that's a fundamental thing. And Kafka is a tool we've used to free ourselves from that communication between services. So it abstracts it out, having a ubiquitous way to communicate events, data between services, allows us to take it up a level. We also do it in the organization. We actually have communications, ubiquitous communication tools between people and teams. We actually use Slack, but that's another story. So by introducing this and abstracting ourselves up, we can now allow teams to develop microservices in whichever way they wish, in a fashion they wish, and it's not constrained by the organizational boundaries, is what we believe. So that's the problem set. Kafka is one of the tools we've used to break that problem set and allow us to go forward. So how did we do this? So it started with that one piece of culture, one team, where we started developing a solution, and Kafka was introduced into the organization. So this came about with one team looking at clickstream data from our website, sky.com. There's only one team, so they were focused on one aspect, like looking at just one aspect of a human body. They were focused on that. They started developing, using it, and what actually happened was we said, you've got a problem. You can't look at the data holistically. We can't understand users' behavior. We have a lot of data, different systems spread across, different vendors, different solutions, no way to marry the information together. So they took this problem, we left it to the engineers, and they came up with a solution. It took them 2 weeks to implement Kafka, took the open source solution, put it in place, got it up and running in 2 weeks, proved the principle, which allowed us to remove all of the tools that had been overloaded onto the platform, and actually stream to an analytic system, which allowed us to connect information. That went into production, I think, roughly within 1 month from the initial idea that the engineer had. To this day, 4 years later, that system is still used within Sky, connecting all of the websites together, collecting clickstream data and tagging information through a set of libraries which they produced, which have been reconsumed by multiple other teams onto devices, mobile devices, etc. And it still runs today and is still used. What it triggered within the culture was they took ownership of the problem, they took ownership of the data, and then, back to the thing about the tools influencing what you do, it started modifying their behaviors. It started modifying their business behavior because suddenly this was available to them. They could actually look at it and come up with other ideas. And the system has just developed over the last few years and continuously built up to influence actually the way we organize our websites, influence the way we click data on the system, influence the way we analyze it in the background, and actually moving it towards real time. Now it actually is real time. So that's one team. Oh, before I move on, they also started internal open source. So it was the first library and project inside Sky that we open sourced internally for the community to build, for our community to build. which is one of our engineering principles as well, part of our culture. Internally, we effectively open source, share across all development teams, and allow them to contribute back. But as I mentioned, this is one team. The way you influence an organization, though, and a culture within an organization, is you have to be able to expand it beyond. You have to be able to take it to all the teams. Same as a community. The idea may start with a small group of people, but you need to be able to build a community around it. You need to be able to spread that culture and that knowledge. So how did we do this? Well, we look at it as basically creating an ecosystem. That team started off with a library. They started off with a particular way of doing it. They took hold of the problem, and they solved it, and then they shared that knowledge. Within Sky, one of our fundamental things is we are a DevOps culture. So this means you build it, you run it. All of my development teams are operationally responsible for our systems because it builds certain behaviors. It builds, if you're going to be woken up at 3 o'clock in the morning, you're going to make sure that's going to work well. You're going to make sure the testing is done fully. You are going to make sure the monitoring is in place. You're going to make sure it auto-recovers and you don't even get the call. So we built this into our culture. However, one of our teams took this a step further, and it was actually a team which uses Kafka. Because of the nature of Kafka, distributing data across the system, basically streaming data and events, rather than I'm going to solve my problem and I'm done, they took it and said, when I face the issue, I'm going to fix it, and I'm going to make it so I can share it. So they started building libraries, primitives, particular patterns about the way to consume Kafka and the way to use it within our systems. So they extended our DevOps culture, added to it. And this was a team that basically, they run our, refer to as content discovery. So when you go into a Sky product and you see all the images and Rails across the Sky product, whether on a mobile device or in your set-top box, those Rails are driven by that team. Millions of customers needing individualized information and personalized information about what they wish to see. So, although they had a massive task to undertake, they had decided when they were doing it to make sure that they were all reusable and they could actually build upon that. And as well as sharing it internally, we have now actually started sharing it externally. These are reports which are available. They're nothing fantastic, but they are a base set of primitives, as I said, and we'll continually build on them. We're going to release more, and we're going to add to it. Part of our culture is to share internally and also share back to the community. So we want to be in the communities. We use predominantly open source software within our entire organization. So we've gone from a small team incubating an idea, incubating a piece of technology, using it, to pushing it out into an ecosystem, and building on that culture, building on the principles that we hold true and the values we hold within the organization. So where do we go next? Well, our next stage is to industrialize this process. And this comes down to looking at those patterns, taking them, making them, expanding on them, making them reusable, as we said, by everyone, but constantly expanding on them. We as engineers, developers, work based on patterns. That's object-oriented design, the gang of four. It comes in patterns. We define a pattern which is reusable across multiple scenarios. So that's what we're aiming to do. Internally, I want to do this because it helps my teams not reinvent the wheel every single time. The other part about industrialization is we need to be able to make it scale. Because of the way we've grown it up, which is great, what I've ended up with is I've got a Kafka cluster in digital web systems, Kafka cluster in my content discovery, and a Kafka cluster in my video platforms, entirely separate. They communicate, but they're entirely separate, run slightly differently. So we're looking to how do we approach this appropriately across the organization? And again, because I want that ubiquitous communication to free teams from being siloed and that impacting my product, what I want to be able to do is take it and say, how do I make it ubiquitous? How do I make this a common part of my entire platform and run it at the levels of reliability I require it to be? So that's where we're heading. The reason we go down this path is it's actually one of Sky's company mottos, which is believe in better. This is fantastic from an engineering point of view. It means we are encouraged to constantly push the boundaries, to constantly move forward. And the only way we can do that is by building a common culture, by building a way in which we approach the systems, and a way in which it takes us away from our organization affecting the way we work and affecting what our customers see. My job as a manager of development teams is effectively to influence this. It's to the teams and the community to develop it and to get it in place. But for me, I set the ethos and nudge and poke and prod people in this direction. But it's fundamentally my development teams, my engineers, my principal engineers, my architects who drive this forward. And it has to be embedded within the organization. So Kafka is one of the core elements which has helped us move down this journey. There are other tools that have gone through the same journey. So we have done the same with Kubernetes. We contribute back to the Kubernetes open source. We've done the same with Cassandra. We've done the same with Couchbase. We work our way through in a very similar manner to all of these, and they become core to our systems and our services. And what we refer to as our core platform is built up of all these tools. However, we always go right back to the beginning and say, it's okay to challenge. The tool has to be fit for purpose, has to meet what we need. So, to us, the reason we concentrate on this, we ensure it's embedded within our organization, is because we have a lot of products that we have to support. And we have been very successful in doing so over the last 4 years. These are all the products which are my platform and my team has successfully been able to develop against. These are all across Europe, so we deliver services right across Europe. We have over 200 linear channels, so this is your football event. Our systems have to be able to respond to millions of users coming on within a 15-minute time span, and then disappearing an hour later, or disappearing at half-time, and then coming back immediately. The system has to respond to that. We stream billions, hundreds of billions of minutes of content a year, and that's just increasing. Also, having that ability to build services is crucial to us, as I mentioned. I have over 500 unique services, each of them horizontally scalable within my architecture. If I didn't have a way to communicate between those, I would not be able to put this system in place. I then also, and another service which we've actually built in the same manner, where we've taken open source and built and shared that across multiple teams, I deploy, some's a little bit out of date actually, we deploy almost 10,000 times a year to our system. Continuous deploy, continuous delivery. That rate of change is not going to go away. So having that commonality, having it built into your engineering culture is essential. On top of all that change which we have to go through, which meets the need, supplies the customer value, we also have to maintain a high availability. Our target is 5 nines, which really means 100%. You don't get to fail. You don't get to allow the system to fall down. So again, it's another part which is built into all the engineers. When an engineer is building a service, they build in the patterns to ensure that the service never goes down. Or if it does go down, that the customer never experiences it, never sees it. We also, as I mentioned, have to deal with millions of concurrent users. That football match scenario, or Game of Thrones. Don't know how many fans of Game of Thrones is in here. That is probably the most tense time within our organization. You don't get to miss it. The amount of bad press we get if we miss the beginning of a football match, or the first season of Game of Thrones, or the last episode, you can imagine if it goes wrong, my phone is red hot. So all of that is built on that culture. We need to do that. And now, with that acquisition of Sky by Comcast last year, we are being asked to take this global. So our systems are being transplanted to the US. Luckily, we are cloud. We go multi-cloud, hybrid, and we can transport our systems, configure them, and set them up in the US. So we are starting to move global with all of what we do. So how did Kafka ultimately, just to summarize out, how did Kafka help us? It helped us by, one, it reinforced that sense of ownership, which is crucial within our engineering culture. So engineering teams have to feel they own the service, own what they're building. That is the only way they will to build it for longevity, have pride in what they do. It also helped us foster a spirit of collaboration. So it allowed teams to collaborate internally, externally, and even out into the broader community. Also, it helped us reinforce that focus on data. Data, from an engineering point of view, is the lifeblood. Understanding what is going on with your systems, understanding the behaviors of your customers, the behaviors of the components within your system, every aspect will allow you, once you can analyze it, to determine where to go. Also, to develop that single ecosystem. And when I say single ecosystem, this isn't building a monolith. This is an ecosystem of tools that we can adapt, build, allow to evolve as we evolve our products, as we evolve our services, as we see improvements in the industry. But it needs to be an ecosystem. It can't be everyone doing exactly what they want in a different way, in a different fashion, over here, over here, over here. That's commonly known as chaos. So Kafka has helped us get to this point. I hope that actually gives you a little bit of insight into what we've done at Sky and how Kafka and this community has helped us. I'm very happy to have presented to you all, and I hope you got something out of this. Thank you very much. Cheers.
Thank you, Keith. All right, now, for our third and final speaker this afternoon, we've already established, we did show of hands before, we've already established that if you're here, there is a decent probability that you watch television. Now, also, if you're at Kafka Summit, I think there's a pretty good chance that you've heard of Martin Kleppmann. Now, he's a distributed systems researcher at the University of Cambridge, author of the O'Reilly book, Designing Data-Intensive Applications, and, as it turns out, personal note, it turns out for me, the most important ideas in streaming, I find out, end up coming from Martin. Now, that's maybe he wishes I hadn't said that, but it's actually true. And this next talk, I think, is a particularly compelling argument that he has to make that you really need to hear. So, Martin.
Hello, everybody. It's lovely to be here. Thank you, Tim, for the introduction. So I would like to start with a maybe slightly contentious question, which is whether Kafka is a database. I mean, I imagine a lot of you will have opinions about what is and is not a database. Some people will come back immediately and say, well, Kafka has no tables, it has no data models, it has no secondary indexes. What on earth makes you think that it is a database? It does not look like a database at all. The only things you can do with it is publish to streams and consume those streams. And you would be right to an extent, but you would also be missing some rather interesting, important ideas. And so maybe just bear with me for the next 20 minutes and we will try to explore some of those ideas. So to start, we have to actually define a bit more carefully what we actually mean with a database. What is it that makes a database a database? And for the purposes of this talk, the definition I'm going to use is a database is a thing that provides ACID properties. So you have probably heard of these in the context of relational databases. The properties are atomicity, consistency, isolation, and durability. And I'm going to go through each of those in a bit more detail and see what those terms might mean in the context of something like Kafka. So I'm going to start with the D of ACID, durability, because that's the easiest in a way. So back in the early 80s, when this ACID acronym was defined, what it meant to have durability back then was that you take your transaction log from your database and you write it to an archive tape. That was the way that durability was achieved back then. Now, tapes have somewhat fallen out of fashion, and so over the years this has become redefined, and so more recently people take durability as meaning the data has been synced to disk. So it has been f-synced in a way that even if that disk loses power, you don't lose the data that you have written to it. And that's a reasonable definition of durability. More recently, again, as we've moved more and more to distributed systems, we've again redefined durability and now often take it to include replication. That is, the data is durable if it's not been only written to one machine, but actually to more than one machine, so that even if you lose an entire server, you don't lose that data. So those things are part of durability, and of course Kafka provides both of those. Kafka will write all messages to disk, and it will replicate them across multiple brokers. So I would say it provides durability under that definition. The last part of durability is perhaps to keep in mind that often if you have data that you don't want to lose, you would set up some kind of backup system so that even if somebody accidentally deletes something, you don't actually lose it. Now, the backup is not really a feature of the database or the system itself, it's a feature of how you deploy it. But certainly you could deploy Kafka in a way where you back up all of the messages that you write to Kafka. And so, again, this provides durability. So that's all I want to say about durability. It's fairly straightforward. Let's move on to the A of ACID, which stands for atomicity. So atomicity is often informally described as an all-or-nothing guarantee. That is, when a transaction writes some data to the database, either all that data ends up being written or none, but you don't end up with some kind of half-finished state where only some of the data has been written, but the other part has not been. So we have to be a little bit careful with the word atomicity because, unfortunately, in different areas of computer science, it means different things. So you might have, for example, come across in the Java standard library, there's an atomic integer class, which allows you to do things like atomically increment a counter, or atomically compare and set the value of a variable. And this is not the type of atomicity that we mean in the context of ACID. So atomicity there is about multi-threaded programming and about concurrency. In the context of ACID, atomicity is not about concurrency. It is about how faults, how crashes are handled. So it means that even if something crashes, the server loses power, the transaction aborts for whatever reason, if the transaction commits, then all of the data written by the transaction is durable. If the transaction aborts for whatever reason, then none of those writes are deemed to have happened. So this is the definition of atomicity in the context of ACID, and we will come back to concurrency when we come to the I, the isolation of ACID. So let me give an example where we need atomicity. So let's say you have a web app that needs to write data to several different systems. So to make this concrete, let's say it's an e-commerce website, you have a product catalog, and you store the contents of that product catalog in a database, quite obviously. You probably also have a cache which may have different presented pre-queried versions of that data. So maybe you have a cache page containing, say, all of the products from a particular brand or so, pre-aggregated, so that you don't need to make a database query every time you want to look up this data. And then moreover, you might have something like a search index, so that if the user performs a keyword search, types some keyword in the search box, that will be served by a separate index. And so some relational databases do have that kind of indexing built in, but often people will deploy it in a way that, for example, something like Elasticsearch or Solr is used as the indexing system, something like Memcached or Redis is used as the caching system, and some relational database might be used as the primary data store. And so what happens if you need to write to any one of these, say that you want to update the description of a product in the product catalog, that updated description will have to be written to all of these different systems. So let's take here as an example that you want to update the description of a product, and we have time going from left to right in this diagram. And so the user who is updating this description maybe first writes that data to the database, and the database comes back and says, OK, that was successful. And then the user goes, OK, well, I have to also update these various cache entries, and I also have to update the search index so that people can find the product by those keywords. And maybe the update to the cache works, but the update to the search index fails for whatever reason. So maybe the server is currently down, it's currently not able to process any write requests, and so, well, what do we do in this case? What we want is atomicity. That is, we want that this update to description is written to either all of these systems or none of them, but we don't want some of them to be updated and some others to be left not updated. So, well, we could retry the write to the index, for example. Maybe it's recovered, but the index might be down for some longer period of time. So how long do you keep retrying? It's not really clear. Maybe it would be better to actually revert the change that you made to the database and to the cache. But now maybe some other users have already seen that new data that you've written, and so then reverting it again is rather confusing. Now, in general, there has been, for decades, in fact, a technique to solve this kind of thing. It's called distributed transactions, and two-phases commit is like the algorithm behind distributed transactions. And in principle, this algorithm allows you to achieve atomicity across these very different systems. However, in practice, it tends to not actually work very well, because in settings like this, you would need both the database and the cache and the index to all support some form of distributed transactions. And unfortunately, many of these systems simply don't. So Memcached or Redis do not support XA distributed transactions. Something like Elasticsearch or Solr similarly do not support it. So you cannot do distributed transactions across these systems. Even with databases that do support them, often the performance is terrible and the operational characteristics are pretty bad. So people have had really bad experiences with distributed transactions, which is why I propose that we simply don't build systems this way. But we can actually rely on tools like Kafka to build these types of systems in a more resilient way. The way you would do that is, if you want to write some data to the database and the cache and the search index, rather than writing it directly, you actually just package up the data that you want to write into a message and send that message to Kafka. And so this is just a single message. It just gets appended to the end of a log in some topic partition. And that is it. That message is either written or it's not written. Now, if that message is not written, nothing happens. If that message is written, then consumers will see it. And so you could now have 3 different consumers, one consumer that updates the database, one consumer that updates the cache, and a third consumer that updates the search index based on those events, based on those messages that appear in Kafka. And because the message is either there or it's not there in Kafka, if it's there, then all of these consumers will see it, and all of these consumers will eventually apply that message. And so this way, we actually get atomicity. We get the all-or-nothing guarantee. If the message appears in Kafka, it will eventually get written to all three of these systems. If one of the systems has an outage temporarily, say the index stops processing writes for a while, that's all right. The messages are still there in Kafka. Once the system is repaired and it comes back up again, it will just churn through the backlog and process any of the messages that have accumulated during the time while it was down. And because all of these different systems apply the writes in the same order, they are actually going to end up in a consistent state with respect to each other. Let's look at another example of atomicity. So in a relational database, if you look at any database textbook, this is like the standard textbook example that you always see for atomicity, which is a transfer of money from one bank account to another. So the way you would typically do that is you start a transaction, you update the account 12345, and you reduce its balance by £100, and then you go over to the other account with ID 54321, and you increase its balance by £100, and then you commit the transaction. So this here is a standard example of atomicity, because atomicity is really important in this transaction, because if only one of these two writes were to happen, that would mean that your system is either having money disappear into the ether, or it's creating money out of thin air. And both of those are things that we don't normally want of an accounting system. They are considered to be bad things. So we want atomicity. We want to either have both of these updates to happen or neither of them. So we know how we can do that in a relational database. We just wrap a transaction around it. Can we do a similar thing in Kafka? Well, it turns out we can. We'll use a very similar principle to what I talked about just now, where we were updating the various different systems. Again, we will take the thing we want to do, in this case, the transfer of £100 from 12345 to 54321, and we will just write that as a single message to a single Kafka topic. And this message just contains all the information we need, including the sender and recipient bank account, the amount, and some kind of unique identifier, which might just be a UUID or something like that, something that allows us to track that event as it flows through the system. So if that event gets written, then it can be picked up by a stream processor. And this will be a very simple stream processor. All it does is it sees, here we have a transfer event. I'm going to output two other events. One is a debit event, one is a credit event. So the one event is the event that represents the reduction of an account balance by £100, and the other event is the increase of the account balance, the other account, by £100. And we can carry forward the same event ID as we had in the initial event. So now, even if the stream processor crashes, if it crashes halfway through processing this transfer message, so that means it might have, for example, written the debit event but not the credit event, that would be bad, because that would mean we're losing atomicity. But once this stream processor comes back up again, well, it will reprocess that message that was incompletely processed before it crashed. And so it will simply output the same event again. This is a very simple deterministic processor. So it will simply produce duplicate events here. And any downstream code can now see, oh, we have multiple events with the same event ID. They must have got duplicated for some reason. We're just going to deduplicate based on that event ID, and thus the problem goes away. Now, even if you're using the exactly once semantics in Kafka streams, then you don't even need to worry about that, because it actually handles this deduplication automatically for you. But anyway, we now have two separate events. If the transfer event was initially in the log, then these two events, the debit and the credit, will both be in the downstream logs. And so we can now also partition those downstream logs by account numbers. And so that means that all of the events for account number 12345, they will all go into the same partition in Kafka. And so all those events will be processed by any consumers, and you can then have a consumer which actually does the update of the account balance and calculates the account statements and such like. And so that data can then be read by some user who wants to know what is the account balance of a particular account, they can go to the appropriate partition and read the data there. So imagine maybe some of you will have noticed an issue that could happen here. So if the user is reading from both accounts, from 12345 and from 54321, what could happen here is that they see one of the two accounts before this update has happened and the other account after this update has happened. So note, this is not actually an issue of atomicity, because remember, atomicity is about ensuring that both happen even in the face of a crash, whereas looking at these events at one point in time, seeing one of them updated and the other one not updated, that is a concurrency issue. That falls under isolation. However, this is indeed an issue, and it can happen, but let me point out briefly that actually many relational databases, like Postgres, like Oracle, actually by default run at an isolation level called read committed, and read committed allows precisely the same thing to happen. So even if you're using a relational database, like Postgres or Oracle, that most of us would probably consider to have these ACID properties, unless you have specifically configured the isolation level to be stronger, to be repeatable read or serializable, then you will have actually exactly the same issue that somebody who's reading two different accounts may see one of the accounts before the update and the other after the update. So we have atomicity, and I spoke already slightly about isolation. This is about dealing with concurrency. So ideally, in a database, the level of isolation that we want is what is called serializable isolation. And serializability means that if you have various people, various clients accessing the database concurrently, the end result that those clients see is the same as if the transactions were performed one at a time in a serial order, where each transaction has the entire database to itself. So serializable simulates the fact that there is actually no concurrency, even though in reality there is concurrency going on. And serializability is really useful if you want to maintain various consistency properties in your database. So let's have another example. Take again a relational database in which you have users who can register usernames, and you want each user to have each username to be unique. That is, you never want more than one user with the same username to exist in the database. And so you might implement it in this way, that you start a transaction. First of all, you look how many accounts do we have for username Jane, and if this query returns 0, then it is safe to insert a new user account with username Jane, and you can commit that transaction. And if everything is serializable, this will mean that there will never be more than one username with the same name Jane in the database. However, if the isolation is not serializable, you could end up with something like the following. You could have the light blue user who queries the database for username Jane, returns 0 results. Then the purple user comes along, makes the same query, also returns 0 results. Now the light blue user at the top actually inserts the new user for username Jane. Then the purple user, well, it also saw 0 results to its first query, so it also thinks it's safe to perform this insertion. Both transactions commit, and now we've got two users with the same username in the database. This is exactly the problem we wanted to prevent in the first place. So in a relational database, if you want to prevent this, you can bump up your isolation level to serializable, and it will deal with this. Of course, you can have other things like a uniqueness constraint on the database as well, and that will help enforce it. Can we do a similar thing in Kafka? Well, we can. So let's take exactly the same username registration example. We have two users here at the bottom, the red one at the top, the greenish-blue one, and they're both trying to register the same name, Jane. And so we have both of those clients that are trying to register the username send a message to a Kafka topic. Now, this Kafka topic we can partition, and we're going to use the username as the partitioning key. And so this means that any two requests for the same username are going to go into the same partition, but requests for different usernames can go into different partitions. And so by routing all of the requests for the same username into the same partition, if you remember the way how Kafka partitions works, any consumer that reads the messages in a partition, is going to see those messages in the same order. That is like a fundamental property that Kafka provides. And we can use this property of ordering. So this ordering here means that in that partition, either the red user's request or the blue user's request will come first. We don't know necessarily which of the two comes first, but we know that anyone who consumes this topic will see them in the same order, and so everyone will agree on which one it was that came first. So let's say, for example, that the red one came first, and so you can now have a stream processor, again, which takes that topic, it consumes it, and it maintains a little database in which it records which usernames have been taken. And so the red user's message comes first, the stream processor checks its database, sees Jane, nope, no entries for Jane, fine. It emits a second message to another topic saying that username registration was successful. Then the green user's message comes along, gets processed by the same single-threaded stream processor. And now that stream processor has an entry in its local database saying, oh, sorry, I allocated the name Jane already. So to the second user, it now outputs a message saying, error, sorry, that username is taken already. So what we have achieved here, simply by relying on the ordering of messages in a Kafka topic partition, we've achieved the same thing as serializably executing this transaction here. Because the stream processor for each individual partition is just a single-threaded, linear, sequential process, we get serializability because it is, in fact, serial, but we still get the scalability by being able to do lots of partitions in parallel because different usernames, they don't interfere with each other. They can just go into different partitions. So that's handled. The durability, the atomicity, and the isolation just leaves C, the consistency. And this is a little bit of an odd one out in the ACID properties, because in fact, the consistency property is a property of the application using the database. It's not so much a property of the database itself. So typically, consistency is understood as meaning that you can enforce certain constraints or invariants, and if transactions modify the database, then those constraints remain true. So we saw just now having a unique username is a constraint on the database. You want there to be no duplicates. You might imagine a similar constraint would be if you're selling seats in a theater, then you don't want more than one person being sat on the same seat. That would get uncomfortable. Same thing about selling seats on an aeroplane. You don't want to give the same seat to more than one customer. These are all examples of essentially the same thing. There's a uniqueness constraint that we want to maintain. Another example of an invariant might be in a financial application that an account balance must never go negative. And this, again, is actually essentially the same thing as the unique username example. You want to serialize all of the transactions for a particular account and make sure that none of them takes the balance negative, that anyone does try to take it negative, it would get an error. So where does this leave us? We've talked through the 4 ACID properties. Does this make Kafka a database now? Depends a bit what you mean, of course. My preferred definition would be maybe that it's not exactly a database, but Kafka gives you the building blocks that allow you to do something that looks very much like transaction processing in a way that looks a bit like a database built out of Lego block components. Those Lego blocks are, in fact, streams, queues, that are connected with each other through stream processors. And so you can, rather than writing a transaction using SQL, what you would instead do is break that logic down into this pipeline of stream operators. Now, I recognize that this is a more complicated, it's a more low-level programming model than simply writing an SQL transaction. On the other hand, it does have the nice property that it scales amazingly well and the performance is excellent, because we're just relying on Kafka and Kafka Streams' own performance and throughput, and they are excellent. And as I showed you today, we can actually achieve some rather strong consistency properties. In fact, stronger consistency properties than you get from many distributed data stores that might call themselves databases. So if consistency properties are what makes you think that it makes a database, then we're actually not too far off here. If you find these ideas interesting, if you want to go a bit deeper, we wrote an article about this, which you can find online under the title of Online Event Processing. Our idea here is that this is actually a different way of building systems. We have online transaction processing, OLTP, we have OLAP, and it seems like there's this emerging third way here, which we call OLAP, Online Event Processing, which is taking these transaction processing-like ideas and implementing them on top of event-based systems. So that's all for today. I hope you found these ideas interesting. The last thing I wanted to just briefly mention is that I will be giving away signed copies of my book later on at 1 p.m. at the Confluent stand, so see you there if you're interested in one of those. Thank you very much, everybody.
So you're probably thinking about that. You're thinking, wait, can that actually be true? Can Kafka actually exhibit ACID properties at scale? You're going to try to poke holes in it. You're going to think about it like tonight. And some night, a few nights from now, you're going to realize, no, you can't. That's actually true. So thank you, Martin. A little bit of housekeeping, just about ready to go. I know it feels like you were just eating those little breakfast sliders like an hour ago. There's still food. So before we get to the food, a little bit of housekeeping. We are a 4-track conference, and again, the schedule is in the app. Go to the session you'd like to go to. You don't have to do anything, just walk in to the room. And for all of the sessions that you don't get to see, that's the other 3 of them, they're being recorded, and within a few weeks, you'll get an email. You'll have access to all those videos. So don't worry about that. You can see every single thing. You're here, and that's good. If you want to be there, San Francisco in the fall, September 30th and October 1st, make plans, mark it in your calendar. It would be great to see you again. And I don't need to remind you about our sponsors because I already saw you interacting with them before we got started here this morning. I put it on Instagram. It's on the internet. So you already know these folks are here. But I want to say thanks to them, and you should say thanks to them, and you should talk to them because they help make all this possible. So a great thanks to our sponsors. And with that, please go enjoy lunch and enjoy Kafka Summit.
Please join us for lunch before starting sessions at 1:30 p.m. Please check your mobile app for all scheduled details.